Have you ever just stopped to think about how all of our modern tech just works perfectly in sync? I mean, your phone, your computer, your watch, everything just operates with this flawless, invisible timing. So, what's the secret sauce behind all that digital harmony? What is the secret to that perfect rhythm? I mean, how does a processor know exactly when to process the next command? Or how do two different gadgets talk to each other without completely messing up the timing? Well, it turns out there's a hidden maestro conducting this entire digital orchestra. And that maestro, it's a tiny little electronic component called an oscillator. And it's really no exaggeration to call it the secret heartbeat of the digital world. It provides the steady, rhythmic pulse that makes literally everything else possible.
Okay, so what does this heartbeat actually do? Let's break down the fundamental job of an oscillator and, how it creates the rhythm that powers all of our technology.
Its main job is actually pretty simple when you get down to it. It takes a smooth, steady stream of electricity, what we call direct current, or DC, and it just chops it up. It turns it into a signal that goes up and down in a perfect repeating rhythm. And this rhythmic signal, that's what we call alternating current, or AC. And in the digital world, we call it the clock signal.
Now, how do we measure the speed of this rhythm? Well, we use a term called frequency, and we measure it in hertz. And 1 hertz is super simple. It just means 1 complete cycle, 1 up and down per second. So the frequency is literally the speed of that heartbeat.
And this idea is really easy to picture. A low-frequency signal, like the one you see on the left, it's all stretched out. That's a slower, more relaxed beat. A high-frequency signal on the right is all squeezed together, which means a much, much faster rhythm. To put it simply, the higher the frequency, the faster a device can think. And just to give you a sense of scale here, let's look at a super popular gadget for hobbyists, the Arduino Uno. It usually uses an oscillator with a frequency of 16 megahertz. That's 16 million hertz. That means its processor is getting a new beat, a new command to do something 16 million times every single second. That's just incredible, right? So, how on earth do we create a beat that's so fast and so incredibly stable? Well, most modern electronics rely on a special material that has almost magical properties, quartz crystal. Let's take a look at how this thing actually works. The secret is in this fascinating physical principle called the piezoelectric effect. And it's a two-way street, which is what's so cool about it. If you zap a piece of quartz with electricity, it physically bends. But if you do the reverse, if you physically bend or squeeze it, it generates its own little pulse of electricity. It's this property that makes it the perfect material for a stable clock. So how do we use this to get a continuous beat? Oh, it's all about a brilliant little feedback loop. First, an amplifier circuit sends a little signal to the crystal, which makes it vibrate. As it vibrates, that piezoelectric effect kicks in, and it generates its own electric pulse. That pulse gets fed back to the amplifier, which boosts it and sends it right back to the crystal, keeping it vibrating perfectly. It's a fantastic, self-sustaining electronic heartbeat. All right, now if you've ever actually cracked open an electronic device, you've probably seen a few components that look very, very similar, but do completely different things. And this can be a huge point of confusion, so let's clear it up right now. You'll see these little metal cans or these colorful components, some with 2 pins, some with 3 or 4, and picking the wrong one can cause your entire circuit to just fail. So what are all these different parts and how can we tell them apart? This table breaks it down perfectly. So first up, the crystal resonator. This is just the raw quartz crystal, usually with 2 pins. It's really accurate, but it needs an external circuit to get it going. Then you have the crystal oscillator. This is the all-in-one package. It's got the crystal and the circuit inside, and usually has 4 pins. It's super accurate and just ready to go. And finally, you've got the ceramic resonator. This one uses a ceramic material instead of quartz. It's not as accurate, but it's much cheaper, which makes it perfect for things like toys or TV remotes. Look, here's the absolute simplest way to remember it. A resonator is just the part that rings, kind of like a bell. It needs someone to hit it. An oscillator, well, that's the complete package. It has the bell and the person ringing it, all built into one, ready to make a steady rhythm. And just to add one more little wrinkle, be careful of ceramic filters. They can look almost identical to ceramic resonators, but their job is completely different. They act like a sieve, right? They only let certain frequencies pass through while blocking others. They filter signals. They don't create them. Now, you might think a technology this fundamental is pretty much a solved problem, but it's always evolving. And this evolution has led to a really bizarre, totally unexpected weakness in one of the most popular devices in the world.
So let's talk about MEMS oscillators. MEMS stands for Micro Electromechanical Systems. Basically, instead of a cut piece of quartz, these are microscopic vibrating structures built right onto a silicon chip. They are unbelievably tiny and are now being used in things like iPhones.
But here is the wild part. A few years back, people started discovering that if you exposed an iPhone to a lot of helium gas, like, say, in a hospital near an MRI machine, the phone would just completely die. And the culprit? You guessed it, the tiny MEMS oscillator. So why helium? What is going on there? It all comes down to size. Helium atoms are the second smallest atoms there are. They are so incredibly tiny, they can actually wiggle their way inside the vacuum-sealed case of the MMS chip. And once they're inside, they physically get in the way of the little vibrating parts, slowing them down until the clock just stops. The phone's heartbeat literally ceases. So from the basics of frequency all the way to the weird case of iPhones and helium, it all just highlights how absolutely vital these tiny components are to our modern world. So let's zoom out for a second and look at the big picture. So what's the big takeaway from all this? Well, it's that everything you do in the digital world, from sending a quick text to streaming a movie, it all relies on that one precise, reliable clock signal. This tiny, vibrating component is the true unsung hero, the fundamental pacemaker that makes sure every digital action happens exactly when it's supposed to. Without it, our digital world as we know it just couldn't exist. And that kind of brings us to a final thought. The story of the MEMS oscillator and helium is this fascinating reminder that as we push technology to be smaller and faster and more integrated, we might just stumble upon these bizarre, completely unexpected weaknesses. It really makes you wonder, right? What other surprising interactions between our tiny tech and the physical world are just waiting out there to be discovered?